Welcome to the Math 120 video practice on counting an introduction to permutations and combinations. As you proceed through the video, at times you should pause the video, read the problem, attempt the problem, then watch the video to see what I have to say. Thank you. It is assumed that you are familiar with the fundamental counting principle. That is, I've created a video on the fundamental counting principle. You should have watched that prior to watching this video. In this practice, we will cover two special types of counting problems that are related and involve the concept of order. One is referred to as a permutation, and a permutation of n objects taken r at a time. Permutation is associated with having order. Finding the number of combinations of n objects taken r at a time. Combinations involve no order. We will see in a moment what we mean by order. When selecting from a list where each item is different, then when the order of selection makes a difference, we call this a permutation of n objects taken r at a time. So you're selecting objects from a list of n objects. The objects are different and you are selecting so many of them. An example of a permutation is simply you are judging a contest where you have 7 entries and you need to pick first, second, and third place. So when you select them, it makes a difference. First, second, third. You express a permutation with this notation right here. And it can be calculated by using this formula given here, but it will be assumed that you will be using a calculator to calculate permutations. You are responsible for knowing how to do this. It will not be illustrated here. In other words, I will not be referring to the formula. I will simply tell you to get your calculator out, understand how to work with the permutation function on your calculator. Here's an example. Suppose you need to select first through third place in an art contest with 12 contestants. How many ways can this be done? Pause the video or watch it, but pause it if you'd like to try it. This is a permutation since the list consists of 12 different items. There are 12 contestants. When an item gets selected, it makes a difference. First, second, third. So when you get picked, you're either first, second, or third. So when you get picked does make a difference. When you're picking from different things and the order in which you're selected is important, it is a permutation. And so therefore, since we are picking 12 items, we're picking from 12 items, 3 things, that's our notation for a permutation. Using your calculator, you should get 1,320 different possible ways we can pick first through third place when there are 12 contestants. At a cost show, you need to select first through 5th place. You're choosing from a list of 15 entries. How many ways can this be done? Pause the video, give the problem a try. Look at this problem as picking from a list of 15 different things. The 15 entries we are assuming are different. If not, we would be told. There would be something to indicate that they could be the same. Note that the order of selection makes a difference. Being picked for first is not the same as being picked for third. Thus, this is a permutation problem. You're selecting 5 things from a list of 15. So here's our notation for that. 15 pick 5. When you use your calculator, you should get an answer of 360,360 different possible ways. Now note, one way of seeing that order of selection makes a difference. As different objects are being selected, they are being labeled differently. They're being labeled differently. That indicates order. That suggests permutation. Our next example, we have a table that has 12 different books on it. The librarian asks you to arrange the books on a shelf. How many different possible arrangements are there? What's important here is to note the word arrange indicates order. When you're saying you are arranging something, you're indicating the order in which things are placed makes a difference. Pause the video. Looking at this problem is picking from a list of different things. We're told all the books are different. We also note that there's an order of selection because we are told to arrange the books. So this is a permutation problem. We're selecting 12 things from a list of 12. So our notation is 12 pick 12. Using our calculator, we get the total number of possible ways we can arrange the 12 books is 479,001,600 different ways. That's a lot. Now, when selecting from a list where each item is different, but the order of selection does not make a difference, we call this a combination of n objects taken all at a time. So we're selecting all objects from a possible list of n objects. The n objects are different, okay, and you're picking different objects. But again, in this case, the order of selection will not make a difference. We write this in using this term, this notation here. We say C of n pick all. There, once again, is a formula that one can utilize, but we're not going to do that. We're going to assume you will be using your calculator, and you are responsible for knowing how to do this. It will not be illustrated in the examples. Our first example, suppose you need to select the 3 best art posters in a contest with 12 contestants. How many ways can this be done? You might want to try to pause the video and give the problem an attempt. Well, this is a combination since the list consists of 12 different items, the 12 contestants. When an item gets selected, it does not make a difference. No matter when you are selected, you are one of the 3 best. So being picked first, second, or third is no different. It's not like the earlier problem where first was first place, second was second place. Here, you are no different whether or not you pick first or third. So we have a combination. It's 12 pick 3. Using the calculator, it comes out to be 220 possible ways. Our next example, we're at a car show and we need to select 5 finalists for the grand prize. We're going to choose from a list of 15 entries, and we want to know how many ways this can be done. Pause the video, try the problem. Look at this problem as picking from a list of different things. There are 15 different entries. But the order of selection does not make a difference. No matter when picked, you are in the finals. If you're first, pick third, or pick fifth, you're we're saying the same thing. You're in the finals. So this is a combination problem. Our notation, well, we're selecting 5 things from a list of 15. So here's our notation. Using our calculator, combination of 15, pick 5. 3,003 different ways we can pick the 5 finalists. Now note, one way of seeing that auto selection makes no difference is as we pick objects, we are labeling them exactly the same. You're in the finals, you're in the finals, you're in the finals. We're not saying first, second, third, fourth. We're not saying the best, the second best, the third best. We're saying the same thing as we're selecting. Our next example, we have a table that has 12 different books on it, and your English teacher asks you to select 4 books to read over the summer. How many ways can you select the 4 books to read? Pause the video, try the problem. Here we go. Looking at this problem as picking from a list of different things, we're told all 12 books are different. If they weren't different, then we would have a problem here. It would not be a combination permutation type problem. All the books are different. Note the auto selection does not make a difference. She did not indicate that you had to read them in a certain order. If I picked a math book and an English book to read over the summer, that would be no different than picking the English book and then picking the math book. I am just picking 4 books to read over the summer. I'm going to read this book. 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 I'm not saying I'm going to read this one first. I'm reading this one second. There was no indication of order in this problem, so this is a combination problem. It's a combination problem where we're picking 4 things from a list of 12. Here's our notation. Combination 12, pick 4. Using the calculator, 495 different possible ways. Now here is our challenge problem. This one's a little bit more complex. We have a committee to be formed consisting of 3 men and 3 women. They're going to be selected from 5 men and 8 women. And we want to know how many possible committees can be formed. You can pause the video and try this yourself, but I'll hint the fundamental counting principle is going to come into play. Remember, one thing you consider when working a counting problem is breaking the counting problem up into individual steps or separating it into smaller counting problems, something we're going to do right here. Look at this task as being made up of 2 separate tasks. We need to select the 3 men. We need to select the 3 women. Well, when we go, well, these 2 things are combination problems. Think about it. We didn't say anything about president, vice president, secretary. The 3 men are going to be on a committee. The 3 women are going to be on a committee. I'm saying the same thing. So we know these are combination problems. For the men, you're selecting 3 men from the list of 5. So it's a combination of 5, pick 3, which is 10. For the women, you're selecting 3 things from a list of 8. So that's a combination of 8, pick 3, which is 56. But again, these are the 2 things I have to do to complete the overall task of forming the committee. So by the fundamental counting principle, we can multiply. 10 times 56 is 560 possible committees. But see how this particular problem was decomposed into 2 separate counting problems, each of which happen to be combination problems. Now read this particular problem, pause the video and give it a try. Sounds similar, doesn't it? But what is the difference between this problem and the previous one? Here it is. The composition of the committee has not been specified. In the previous problem, we required 3 men and 3 women. On this committee, we only require 6 people. So it could be all men, all women, 1 man, 5 women, 5 men, 1 woman. We don't specify the composition of the committee. So we have one task, and that task is to pick 6 people for the committee. This is a single combination problem. Once again, there's no order. As I pick, I'm simply telling you you're on the committee. You're selecting 6 people from a list of 13, 5 and 8 women, 13 in total. Once again, we never specified they had to be men or women. So notation, 13 pick 6. Using the calculator, 1,716 possible ways. So in summary, to keep in mind, for something to be a permutation or a combination, we need to be selecting different things from a list of different things. That is, I can't pick something over again. Whatever I'm picking from, everything is different. For example, the following is not a permutation or a combination. On a table, there are 3 letters, letter A's, there are 5 letter B's, and there's 1 letter C. We need to select 4 letters from the table. Since the items on the table are not all different, this is not a permutation or a combination. That is, we're assuming all the A's are identical, all the B's are identical, well, we only have 1 C. So, permutation combination would require everything to be different. So it can't be a permutation or a combination. Here's another example of something that's not a permutation or a combination. Choosing from 26 letters of the alphabet, we need to select 4 letters to make up a password. You may use a letter more than once. All the letters I can pick from are different, but I can pick the same letter. So this cannot be a permutation or a combination. When you're talking a permutation or a combination, you're picking from different things and you're picking different things. So you can't pick things over, and again, you can't have something identical to pick multiple times. Now, I'll conclude this section with a simple comment on factorial notation that you see in the formulas that were presented earlier. But once again, I am working on an assumption that you are working with a calculator. But you will see this notation. I'll simply tell you what it means. We define 1 factorial to be equal to 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1 times 3 times 2 times 1, which is 6. 4 factorial, 4, 3, 2, 1, 24. 5 factorial, 5, 4, 3, 2, 1, 120. And 0 factorial is defined as 1. So you get the pattern. That's what we mean by factorial notation. It is useful in counting, but I'm not going to discuss it here because once again, you will be working with your calculator. So, well, this is just a summary of what I just said. Well, this concludes this video. I hope you find it useful, and thank you.